Hola clase! Today we're going to see how to solve a full trigonometry problem start to finish. I've copied here the diagram we have from the notes, and they tell me what they need to divide this field in 4 paddocks, minimum 2000 square meters, ideally just by fencing the diagonals. So if I'm going to have to find the length of diagonal fences, the areas, and if they're not big enough, an alternative. So there's going to be my achieve, merit, and excellent grades, respectively. All right, first I'm going to need to find areas, so I start thinking on what do I know that allows me to do that, which is a formula of the area of a triangle, half b times c sine of a, and to use it, I need one angle and two sides, and they need to be the arms of the angle, the ones that I'm bolding there, which, by the way, is the same combination I need to use the cosine rule if I want to find a side. So everything I do is going to be to find these pieces that I need. So remember, green is what I think. Okay, so I'm going to start finding the fences, which is the first thing they ask me. And the diagonal AC, it's in a triangle where I have two sides and the angle. So I can use a cosine rule. It's the first time I use it in the paper, so I write it here. A square equals b square plus c square minus 2bc cosine of a, just like it shows in the formula sheet. And then I substitute the values. A equals 540 square plus 430 square minus 2 times 540 times 430 cosine of 70, all of that square rooted, which gives me 563.63 meters. And I need to round, but I give myself a couple of decimal points because I know I'm going to have to use it later, and I don't want to round too much. And always remember units throughout. I have one, now the other one. BD belongs to two triangles, ABD and BDC, and I need either side angle side or the opposite angle to the side I'm looking for, and a pair of side and angle, one to use the cosine rule and the other to use the sine rule. In ABD, I have this side and this, no angle. And in BCD, this side, this one, and no angle either. So I think I'm going to find this angle A here, and then I could have the pieces I need. I'm drawing the diagram here again. Remember, this is in my head while I think of my strategy. So far I know all 4 sides and one of the diagonals. I have 2 triangles with all their sides. So if I could find these partial angles, one in each triangle, I could have it. Everything that is not in the original diagram, I name. In the real paper, you would just draw it in the original here, A1 and A2. I'm doing it anew, so we don't have to be scrolling up and down all the time. Now that I know what I want to do, I have to write it in the paper. So blue is the ink. A equals A sub 1 plus A sub 2, and I start with A1. I'm quickly drawing a triangle that has it here, so you can follow. And I'm finding an angle. It's the first time I use the formula, so I write it as it is. Cosine of A is b squared plus c squared minus a squared over 2bc, and then substitute. A1 equals inverse of cosine of 270 squared plus 263.62 squared minus 370 squared over 2 times 270 times 563.62, and that is 33.54 degrees. Same deal with A2, which is in this triangle here that I'm labeling quickly, so we know what we have. And there is a pair of side and angle here, and I know the opposite side to the angle I'm looking for, so I'm going to use the sine rule, because remember I need 3 different methods at least, and I haven't used that one yet. Same as before, because I haven't used the formula, I copied sine of A over A equals sine of B over E, and then substitute. Sine of A2, which is what I'm searching, over 430 equals sine of 70 over 563.62, and then I rearrange. I'm doing it here so we don't have to scroll. A2 gives me 45.80 degrees, therefore A equals 33.54 plus 44.80, 79.34, and I round to 80 degrees. Now remember what I was finding this angle was to find the diagonal, length BD. And now I've already used the cosine rule, so I don't write it, I just substitute into 270 squared plus 540 squared minus 2 times 270 times 540 cosine of 80, all square rooted, equals 560.24 meters, again rounded to 2 decimals. Right, that's my achieved grade there. I've used 3 different trigonometry rules to solve a problem, even if I'm not finished yet. I'm going to scroll down, and now I'm finding the areas. Always label what you're doing, and again, I'm copying what we have so far. In paper, you would be labeling one diagram as you go. Now, I not only have the original sides, but I know this diagonal, the 563.62, and this one, 560.24. I'm not putting units so it doesn't get very crowded. And I also know these two partial angles, A1 and A2. Now with all of these, I need to find areas. So I think how I'm going to tackle it before I start writing. For me to use the formula of the area, I need a side angle side combo. So I start looking at the 4 triangles to see if I have all the pieces. I call this point, remember everything that it's not in the original diagram, you have to label it. So I'm going to call it M. In ABM, I have this side, this angle, but not this side, the length between A and M. In AMD, I have the angle, one side, but again, not the other. In BMC, I only have one side, and in CMD, the same. So I think I need to find the missing sides between the corners and where the diagonals meet, and the partial angles. How am I going to do that? Well, I know angle D, so if I could find D1 and D2 with a cosine rule, and then with D1 I can find B1, the partial angle on the top, and angle B is on a triangle with 3 sides known, so I can find it. And then the difference is the remaining angle in B2, which then I can use to find C1, the piece that I realized in my tiny diagram that I was missing. And with all of those partial angles, I can find the angles that the diagonals made with each other, angle AMB, AMD, etc. Because then I will have a pair of side and angle that I know in each of the triangle areas, and one opposite to the side I want to find, and I would have all the pieces I need. Okay, that sounds like a good plan. I'm ready now to start writing. I'm going to calculate angle B first, and I'm quickly drawing the triangle I'm using so I can substitute easily. This is again a cosine rule, so I'm not going to write it. I'm just going to substitute. It gives me an angle B of 122.67 degrees. Let me scroll down. And now in triangle BCD, I want to find this D1, which I'm labeling so the reader can follow me. Remember, always label everything. And it's again another cosine rule because I know the sides of the triangle. D1 gives me 41.42 degrees. And to find D2, which could be the other part, I subtract from 70. It gives me 28.68 degrees. And because interior angles in a triangle add to 180, B1 is 180 minus 80, which was angle A, minus 28.68, which is 71.32 degrees. I know the whole angle B, so B2 is B minus B1, and that is 51.35 degrees. And you will realize I'm always showing my working to justify my values. I need to show what numbers I'm using. If it's not on the paper, I didn't think of it. And lastly, angle C is 180 minus the partial angles, B2 and D1, and that is 87.33. We're almost there. Now in triangle ABC, I have all three sides and two of the angles. So I can find C1 very quickly by subtracting from 180, and that is 23.78. Or you could use the cosine rule, which is what I did in the notes, even if it was a simpler way. And then with C and C1, I get C2. I've summarized here all the values we have. So again, we don't have to scroll up and down. We know all partial angles, so we can find the angles that the diagonals do with each other in this intersection M, which I need to have the pair of side and angle values. That's nothing fancy, it's just applying that interior angles in the triangle add to 180. And with that I find angle AMB, and because angles in a straight line add to 180, then angle AMD is 180 minus AMB, which is 104.86 degrees. And this one I don't need it right now. I will use it in the excellence section, so it will make sense in a minute. For the length AM, I'm going to use the sine rule to find a side. Because I haven't used it yet, I'm copying it here. And what I need to substitute, if we draw the triangle here on the side, label every value I have so far. This is the side I'm searching for. And I have the opposite angle, B1. And I have this pair of angle and side. So the length AM over sine of 71.32 equals 270 over sine of 75.14. I rearrange, the sign passes multiplying, AM equals 264.63 meters. With that length figured out, the other segment is 563.62 minus 262.63. That equals 298.99 meters. And in the same triangle, ABM, I know A1, so I can repeat the entire process and find the other side of the triangle, BM. So this is the same idea. We rearrange, and BM equals 154.34 meters. And then we can get MD by subtracting from the whole diagonal again. Okay, with that, we've got all the pieces. Now remember that what we want are the areas of those four paddocks. So I put the formula I'm going to use here, and then I start substituting. I start in order. Area of A and B equals half of 270 times 264.63 sine of 33.54, which equals 19,738 meters square. I'm rounding to whole numbers. And then I'm just going to do the same for the other three clockwise, BMC, CMD, and DMA. Okay, that took definitely more than one screen and 10 minutes, but we have everything we wanted. The last step, being tidy, to collect all the results together, nice and easy to find. So this is just copying all the values for the diagonals, the four areas, box it, and it seems that we're done. This is my merit right here. I gave the solution. But now there is one area that is actually smaller than what we need. The excellence is going to be finding an alternative, and for that there may be several options. I'm just going to give you one. So I make another heading, and I need to explain my thinking, why I'm doing what I'm doing. That is my proof of abstract thinking. I'm taking into account the factors of the problem to find a better option. So I start explaining that paddock A and B is too small, and because it's next to A and D, which is plenty big, I'm going to move the fence. I'm drawing a quick sketch so the reader knows what I mean. And now I could eyeball it and see what happens if I move by a certain amount. Give the numbers, go for it. Instead, I'm finding the minimum it needs to be moved. And this is an overkill, by the way, okay? Eyeballing it and finding a solution would be perfectly fine. Anyway, I found the area that I need to give to paddock A and B to make that 20,000 square meters. That's just 262 square meters. I know the formula for the area of a triangle. I'm going to use it and say that both sides are the length of that half fence between them, AM. And if I make an assumption, I explain it. With this tiny area, it's almost an isosceles triangle. So then I rearrange, get a value. I need to make the final statement, so I just put that in a sentence. Moving the fence by 0.42 degrees towards D and joining it with the other diagonal, because I don't want to be working with sectors, will create the necessary space. Now, half a degree may be fidgety, so I can say that because the paddock A and D is much bigger than the minimum 20,000 square meters, the farmer may want instead to move the fence along the other diagonal a given value, knowing that there is space. And if I propose something, I need to give values, so I show the numbers for moving it by 5 meters. If the fence is moved 5 meters, then I would have a triangle with the sides 264.63 and 5 meters, and an angle here of 104.86 degrees. Remember, we found it before to have it ready. I have all the values to calculate that extra area. Substitute area equals 639.5 meters square, and then make the final statement, just a couple of sentences. This way, paddock A and B would be 19,738 plus 640 square meters, or 20,378, and the new paddock A and D, it's still 52,595 minus 640, 51,955 square meters, well above the minimum. All right, so with everything put in paper, I have proof of my solution, my abstract thinking. I found an option that complies with everything we needed. Now we are done. Now it's your turn to go and practice. Thanks for watching.